Right. We've got all right. Brian Chapman's here. Uh, well, he's getting here. Yeah. Uh, wait to see that he's connected. Hmm. Well, welcome to Brian. It's 6 o'clock. I think it was Brian who sent me an email just a little while ago. I haven't replied to that one, but I hadn't forgotten your situation. I just wasn't caught up in my mind with it. So yeah. Uh, yeah, it looks like I got a last week on Wednesday I was looking at a difficult I was looking at meetings on Thursday and Friday and a makeup class in another course, and so I had a real busy few days, whereas this week it looks a little simpler for me. Uh, um, and we'll see. And let's see, Thanius, admit, and uh, Shalab, admit. Okay. Um, another reason why uh, uh, another reason why is it's exam week in my courses as far as my scheduling stuff. So maybe less work. Just have to send out an email or two reminding people that there won't be any uh, lecture. But okay, so uh, why don't I go look at my slides? And hide video panel. Uh, we've got manage participants. Okay. Tyler, admit. Okay. Uh, did I click the control? And hide floating. You know. Okay. Well, it's April 28th. Had uh, some news that Bernie Sanders dropped out of the race. So uh, thinking of knowing what our some of what's going to be in our ballots in November, and yeah, I don't know how things will play out for that. Um, we'll uh, and still some um, I guess some news about the COVID-19 is, although I guess yesterday was a record death in New York, the hospital admissions seem to be uh, flattening, uh, uh, which is somewhat of a good sign. Uh, okay. Um, we'll talk about some of the organization of the class and then a little start on chapter 15, acceptance sampling. I've got like 60 slides today, and although I had them prepared from older places, they may not be as good as I'd hoped. Uh, assignments and changes. Well, I I've been getting sort of strange concerns about what to do about Zoom bombing. One um, one email at Oglala Lakota College said I should restart my classes and to make sure there's no offensive Zoom bombing stuff. Restart my schedule of the classes. Uh, and that's a concern. Um, Zoom has been in the news. I I think they have information about me for Facebook right now, although I'm not on Facebook. So um, there is a chance then you may be getting an email that says we're going to be using a different um, uh, login, and I don't know how that sits with D2L, uh, or if I can change the settings. Oh, well, we'll see. Those are the three cover arts of the book. Um, I guess strictly speaking, those are copyrighted and illegal. But uh, when it comes to copyrights, if nobody complains, you're good. Uh, and I just don't think John Wiley's going to complain about the cover art of the textbook. Um, our last meeting, our third last meeting was on 3.3, and just remembering back there, we weren't even sure that COVID-19 would come to South Dakota, and was we were planning on coming back 1 week after spring break and all be fine. And now we've had an extended uh, spring break, and we put the whole rest of the semester online and can't really do proctored exams. And I've been through this a couple of times. Essentially, if you go through where the exams are proctored, it's pretty likely those places are closed down. Uh, so it won't work so well. And we yeah we were thinking business as usual April 3rd and to plan for it, but we we didn't. Uh, and I guess I have tentative ideas on. I'm thinking tomorrow I'll email you a copy of exam and set it up on D2L for you to upload the exam. I have one for the forecasting class, and for much of it, for much of it, um, you could probably it's a Word document, and you can probably type it in Word. And I haven't tried to like upload it to Google Sheets and see what it looks like. or Google Docs, just in case. I don't know. You're working with a Chromebook, uh, or something, phone. Uh, that'd be yeah, it'd be hard to look at it in a phone, but um, it's a Word document. You can type most of the answers. There are a few where I ask for some formulas where it'd be a little hard to type some math. Uh, the in the class, um, the forecasting class, um, we uh, you you could do the uh, I'm thinking exam the the example problems for this class though, uh, are all calculation type things, and I'm thinking that we might have a mostly a calculations test, so that gets a little hard to write. Uh, However, you can take pictures with your phone, and there's no limit to the number of files you can upload. But there is a limit to the file size, and that's 1 gig, and it's really hard to get a picture up to 1 gig. I mean, with common with common camera techniques. Um, anyway, that's where we were there. We were asked to end the live login, but that's still been approved to stay forward. So we'll have that. Um, and old comment, my daytime phone. Sometimes my wife my wife will cancel things out if she doesn't see. Oh, my daytime phone. I'm not in the office. Uh, my regular cell, and I hope nobody tries to calling it, but it's across the room now, charging. Uh, although as I think about it, I could have had it charging right here, but uh, I didn't. Uh, and then my home phone. Sometimes my wife hangs up on numbers she doesn't recognize, so if I get to it before she does, that works. Um, Web resources, we're using D2L. It has links. You log in. Currently, that's what's worked, and it works pretty well. And uh, there's a chance I might end up changing that because of Zoom bomb problems, but I don't know. Um, and there are a few other ways to get to the video in D2L. Um, I having just one D2L link is all that Dr. Dubé has, and he's had almost as many students in night classes as I have since he started. Um, what I have been doing is when I had somebody who was working behind uh, the great firewall of China, trying to get to trying to get to my stuff, and I had multiple things, and he was able to get to it. So where are we? We'll do chapter 15 this week. Uh, I won't hold a class on the 15th. Uh, you don't have your taxes due that night. They've moved them back to July. Uh, uh, admit, hey, hey, Ace, just got to this. Next week, I won't be holding any I I won't be lecturing my classes. Kind of treat that. It's fairly common when you give a take-home exam to give somebody a week off or a class session off, just because the take-home exam takes up some time, and uh, you assume they'll spend that time doing that. So we'll have that, and uh, we'll um, and I'm not so sure what I'll do on the 29th. Um, anyway, then finals week's the 6th. Could I use that period, the 29th or the 15th? I could log in and answer questions and just I I guess I could. Yeah, yeah, I could answer some questions. Uh, sure. That I hadn't thought through. I hadn't thought through that, but make it a short 1 hour window. Well, that's uh, uh, Ross. I'm thinking that uh, that's a reasonable thing. I could do something like agree to be on for 1 hour unless um, unless the questions overrun the time limit.
And I agree, Professor. That's why I said you make it a 1 hour window, and if we have questions, because you're going to be giving it to us earlier in the week,
Yeah,
if we can't figure out questions to ask you by 6 p.m. Wednesday to 7 p.m., well, I
yeah,
would say that's probably on us. But it would be nice if you were available in case something wasn't clear or we want some clarification. And all of us would be around to hear what any, could make ourselves available because this is a class period.
yeah, yeah. We could. I could do that. Uh, yeah, I could do that. As if I was in the room with an exam on site. Yeah, I could do that. Uh, I'll I could do that in both classes actually. So maybe maybe I'll craft an email on that. Email on exam answer questions. Okay. So much for the chat. Uh, well, I guess I could also do uh, make the second exam due uh, on the 6th, and uh, or the third exam due on the 6th, and have another question session on the 29th. That yeah, let me consider those things. Yeah, I'm thinking all three of the assignments will be equally weighted, but I don't have that written down. Maybe I should put that in emails. There are suggested problems with solutions, mostly that were given by the textbook. and they are in D2L. So hopefully that'll help you uh, in preparing your take-home exam. And I haven't done any demos in R yet in this class, although probably could see. Lot by lot accepted sampling by attributes. In the when I started working in quality in the mid 70s, summer of trying to think, summer 76, working for General Electric as a co-op student. Up until I went to go back to school, well, go back to grad school in '83 and worked in industry. These acceptance sampling things were everywhere. I mean, anytime all the nearly all the inspection that wasn't done 100%, and usually when parts were moved from work area to work area, there was an inspection by acceptance sampling plan done. So, and when parts were coming into the plants I worked in, you know, these kinds of things were very common. And in my first course in quality in fall of '77 at General Electric, we we use these things quite a lot. And guy who worked in the next building actually wrote the book on them at the time, or just slightly after that. Ed Schilling, and it's a monograph from, yeah, I don't know. I probably, I'm curious. I have a web browser. Um, yeah, why don't I get a new share, and I've got that, and I've got browser and Schilling. Schilling acceptance sampling. Acceptance sampling for quality control. Oh, there's a second edition. Oh, I wasn't aware. So, acceptance sampling and quality control. Maybe I was aware. So, well, that's what it looks like. Schilling, the first author there, was and worked for GE when I was a co-op. And does it say anything? 700 pages hardcover, so it's a big thick book. Chapman and Hall, CRC Press. In 2009, it was in the second edition. So there is hardcover 79, I think there's a mistake there on that paperback size. Uh, the $890 for their so I don't know. Used hardcover 221 new. Um, so not real popular book, but so there has been one whole book 2009 written about the subject of acceptance sampling. Uh, and no, Ed Schilling, is he still with us? What's it say? I don't know. Uh, doesn't say anything there. And new share. Uh, lot by lot acceptance sampling. Um, yeah, Ed Schilling was well established in his career when I was 20 years old. So he, I'm guessing he's probably at least in his 40s by then. Yeah, he may have passed away by now. What will we look at? We'll go to we'll look we'll, we'll talk a little bit about the first 5 sections here and not get into the supplemental stuff. Maybe some of the topics like this lot formation won't talk too much about. Um, now, yeah, like I said, this was extraordinarily common uh, uh, in the 70s through the early early 80s, and then people tended to want to move away from it. Um, uh, for a few reasons, particularly when you did the attribute stuff, you were actually accepting parts you knew you were that were bad, and uh, that didn't look so good, or out of spec. Uh, yeah, we'll talk a little bit about that, or I'll ramble. I don't know. Uh, goals. We'll find out what acceptance sampling means and advantages and disadvantages of sampling, difference between attributes and variables, no single, double, sequential plans, the importance of random sampling, understand uh, parameters, uh, performance, know how to design. It will My internet connection is unstable. I just got a message that went away. So we'll see. Uh, uh, maybe I should switch the room I'm in. Uh, I'm thinking maybe I could use my daughter's bedroom, if being she's away and hasn't been home since uh, around Christmas time. Uh, and oh, another chat message. Sounds like a great deal. Okay. All right. I don't always. Uh, let's see. Want to see my title? Oh, uh, acceptance sampling problem. Uh, typically, acceptance sampling is for lot deposition, sometimes referred to as lot sentencing for receiving inspection activities. So you you may be in a situation where you have a loading dock where you receive parts. And when I worked for GE, that was there, and most of the parts eventually went to many of the parts soon after they were received went to incoming inspection, where I was actually had my desk in incoming inspection area for a while when I worked for GE. Um, and there are people who would apply this acceptance sampling. They would um, they would open boxes and sample parts from them. They would inspect them in the procedures that was there, and they would then accept or reject the parts based on the rules they used. Accepted lots are put in to production, and rejected lots may be returned to supplier or subjected to a lot deposition action. So, in other words, and another place I worked, uh, Eaton, uh, and yeah, uh, you would put these parts that were rejected, and if they were internal rejections, then um, if this was done between areas of the same plant, you would have people arguing about what should be done with rejected parts, and or what do we say? Rejected lots, uh, and this uh, doesn't always. When I was at GE in the plant I was in, many of the parts that came into our plant were made um, eh, by plants in like the same county. So these uh, they were within in GE rejections. So wasn't like you had big slews of lawyers involved, usually just engineers. Um, so sampling methods may also be used in various stages of production. Uh, they're designed to sentence the lots, okay? Either we accept them, put into production, or reject them. Uh, and this kind of procedure causes delays, and it causes um, a lot of things to be sitting around, and uh, it it also leads to more inventory because you have to plan for every so often you're rejecting a lot and delaying what you do with that. So the acceptance sampling plans are not designed for estimation purposes. So when you go through and try to say what is we don't really know the uh, percent conforming or the percent non-conforming after we apply the sampling plan. Um, The truth of the matter is, accepted lots, we could have an ongoing process, and it could be in control, and just every so often we'll reject one. Or we could have an ongoing process. It could be in control, but not meeting our specs. And we could reject most of them and then have a few that pass. Um, Acceptance, yeah. So these are in the sense that they'll uh, affect the process. They're usually much, much later. Uh, uh, but rather as a audit tool to ensure that the uh, output process conforms to requirements. So you can put a lot of effort into acceptance sampling and not necessarily get into changing the process at its source. Um, when sampling plans can be useful. One time you do want to do acceptance sampling in some manners is when your tests are destructive. Sometimes you have to run a test, and that's it. So you can. A common example is bullets. There are certain things you can do with a bullet. When you fire them, they are single-use objects, and if you test to see the way bullets are fired, you can't use them anymore. So you have to do acceptance sampling on your bullets, um, or other things that are destroyed in the test. Sometimes the cost of the 100% inspection is very high. Um, some tests might require you to, you know, uh, put the parts in an oven refrigeration kind of uh, test setup for a week. You know, uh, those uh, those kinds of tests you you can't do 100%. Uh, okay, calendar time. Uh, what would There are many items to be inspected, and the inspection rate is sufficiently high that 100%, a higher percentage of defective units would be passed, would occur. All right, your inspection error rate is so bad that you really, really don't want to do 100% inspection. Uh, so you might end up passing more stuff than you would with a sampling plan. Now that just sounds. I haven't run into that. Um, now this is a way to sort of uh, cut a supply or a break. Uh, you don't have to do 100% inspection because um, things are going well. Um, in the same way, things are still going well, but there are liability risks. So in other words, you didn't inspect these things at all? No, the supplier's just all wonderful. And uh, you don't want to be in that situation. If there's liability risk, we'll say we did sampling according to this level, and uh, you know, hopefully, you know, we haven't had a defective part in 5 years, but uh, let's see, when acceptance sampling is contrasted with 100% inspection, it has the following advantages. Usually cheaper to sample, uh, less handling of the product. Uh, Sometimes handling the product can be um, biggest source of the um, problems with it. Um, uh, it's applicable to destructive testing. So 100% inspection, you can't do a destructive test. Um, get by when you do sampling with fewer inspection, fewer people doing the inspection. Well, often reduces the amount of inspection error. Um, you have fewer inspection tasks being done and they're modest size rather than the 100% inspection. The 100% inspections, um, the 100% inspections are um, often done by the operators, and sometimes their production rates are tightly controlled, whereas the um, inspections are off the sampling inspections are often done by floating inspectors, so you slow your uh, production flow to get likely a better uh, um, you to reduce possibly inspection errors. Uh, Often in plants, a inspector is a higher level job than most of the production operators. So that's and so you usually get someone more experienced doing it. The rejection of entire lots as opposed to simple return of defectant often provides a motivation for the supplier for quality improvements. Well, that's the idea. So you send the whole box back, and uh, you get in an argument. Um, um, and it creates a bit rather than you just get a few and they send you a few more, and uh, uh, to catch up, or you adjust your payment schedule. That seems to have less effect on changing things. Although in this supplier situation, that rejected lot could time wise be very far from um, what the producing organization would have to deal with. So here there are some disadvantages too. Uh, you make mistakes. Okay. Um, every every so often you'll accept lots that have more defects than you thought you should allow, and you'll reject lots that have fewer defects than you believed you could allow. Um, and particularly on the attribute stuff, you don't find out much about the manufacturing process with acceptance sampling. With accepted sampling requires planning and documentation of a sampling procedure. So you have to come up with a sampling procedure and rules and policies, whereas 100% inspection, you just have to show you how to operate someone how to operate the equipment and store the parts as appropriate. Well, there's a trade. No inspection or 100% are probably the most common ways we go about life. Either check them all or ignore them all. But the acceptance sampling gives a middle ground, and we can come up with a sampling plan that we believe is fair for both the producer of the lot and the consumer. You might be able to encourage suppliers to improve the production process. Okay, there are types of acceptance sampling plans. So one major classification is variables and attributes. The variables in this case are the common continuous measures, the lengths, the weights, the resistivities, um, and so forth. Attributes are the decision whether it's just good and bad. Each part is either rejected or accepted based on whatever contributor. Another is the number of sampling. Actually, this is probably better to think of number of samples required for the decision. So there are sampling plans that work this way. We take a sample, we run our inspection, we count the number of non-conforming parts, and then we make our decision. A doubling sampling plans, you take your first sample, and there are then two decisions you make. One is you can reject a lot, or you can accept a lot, or you can take a second sample. And then at the second sample, you either reject or not. This double sampling plan can be extended another step or two or three, and you have multiple things. As discussed in quality control, we can actually go to, and this is not so common with attributes, but with variables, a little more common. We can have sequential sampling plans where at each part we decide to either accept, reject the lot. At each part we decide to either accept or reject the lot, or go on and inspect another part. So and yeah, so these have been around a long time too. Again, for very high cost or destructive testing, those are that way. The procedures Um, what I forgot what I wanted to say. So single, double, and sequential sampling plans can be designed to produce equivalent results. Yes, you can get the same results of accepting and rejecting at the same quality level, but often the multiple sequential will have require less parts on average than the single. So there are things to consider: administrative efficiency, uh, who's doing the inspection, do you want them doing that? The information improves, produced by the plan, uh, to try to uh, calculate in multiple uh, uh, to try to calculate the percent defective in any of these plans is a little bit difficult, particularly if you have some rule like, well, how many parts were really bad, and someone tells you to quit before the sample's done. That's entirely possible. Uh, it's a little hard to decide how to estimate the proportion defective, and also with multiple double and sequential plans. Um, the amount of inspection required by the plan. So how many inspections are there, and is the inspection effort small compared to the administrative efficiency? And then the impact of the procedure on the manufacturing flow. Uh, yeah, the manufacturing flows can get really bad if you have a lot of acceptance sampling done between work areas or between processes. Um, you're, yeah, I remembering back, I got told that uh, we had, like, I don't know, a very modest amount of time, 100 hours of actual processing um, for the parts we were building in one plant I worked at. But it took 8 weeks for the parts to move from the back of the shop to the front, um, mostly because, well, we were doing a number of lots uh, and move lots and 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 so forth. It didn't have to be that way at all. Lot formation and random sampling. This is um, there are a number of important considerations in forming lots for inspection. Uh, this is hard. The lots should be homogeneous. In other words, we kind of would like to randomly sample from the lot. However, uh, you may be told to take 32 parts out of this. What do we have? How many boxes would we have stacked in that cube? Well, how many boxes would we have stacked on that shipping pallet? It'd be 3 by 3, 9 times 4, 36 boxes, and you're asked to do, expect 40 parts. Uh, would you really, really want to open, uh, describe the location of the parts based on, it could be uh, packed in a certain manner where you could actually describe their positions. Would you really want to take apart all 36 boxes and inspect in a uh, in a by selecting purely randomly from what position things were in that cube? Uh, you would spend a whole lot of time packing and unpacking things and reloading a pallet and spending a whole lot of work, and the the boxes on that pallet uh, might not be of trivial weight. So uh, and repacking them might cause problems. Uh, uh, so it it is a problem. The large lots are preferred over small ones. Generally, that's true. Uh, should be comfortable to the materials handling system used both in the supplier and consumer facilities. So uh, getting that pallet of parts arriving and treating that as one lot does get to be somewhat of a problem. You might randomly want to sample one box for the whole pallet and assume that that's fair and representative uh, box in the shipment. Um, and all. However, if you get that one box, most commonly it's one that's on an edge or a corner that's easiest to pull off. Someone might do that. Not really the best practice. You might want to at least dig in and and get another part. However, if the parts fail on the floor, things can get uh, a bit more confusing. Acceptance plan consists of sample size and accept reject criteria for lot sentencing. So that's it. That's what we need in a sampling. Our sample size and how do we accept or reject. Uh, so lot sample size, yeah, there's also an accepted sampling scheme. Is a per set of uh, accepted sampling plans in which, along with 100% inspection and sampling, are related. So uh, we have schemes that actually flip between various sampling plans in various cases, and a system is a unified collection of one or more schemes. So accepted sampling procedures, uh, objectives here: assure quality levels for the producer and consumer, select a plan for attributes, a specific OC curve, and for uh, for the uh, for the attributes, the OC curve is based on the proportion defective. Uh, for variables, for some test statistic, which we have, um, we can have maintain quality at a target. If we wanted something called an AQL system, a term we haven't defined yet, there are MIL standard 105D and ANSI ASQC 714 and similar there. Uh, those are well established procedures, and let's see, participants. What do we have? Somebody drop out? Looked like that. Maybe. Yeah, there's chain sampling when our sampling plans refer to history, and you might actually narrow limit gauging is an idea that you might want to run acceptance system with narrower specifications than you actually use to allow for smaller there. And skip lotting, when histories are very good and you decide not to sample all the lots, so you skip lots. And we also have this idea, the AOQL systems protect the producer in the sense that if they get below a certain proportion non-conforming, they'll have a high probability that a lot's going to work. The lot tolerance percent effective is the other side. This is says that at a certain level, we if things get through our sampling process, we have a high probability that we have at most the lot tolerance percent effective. A simple single sampling plan. Very often n equals 89, small n, that's how many we actually inspect, and c equals 2, that is our maximum acceptance number. So in our 89, we can accept 2 non-conforming and send the lot onward. If we get 3 or more, we reject the lot and treat it as and the single sampling plan, we make our decision to reject a lot just based on the one sample in the single sampling plan. Now, most commonly, people's intuition is they want to design their sampling plans in percentage of lot size. That rarely makes sense because although it may describe your workflow very well, the smaller lots will have the hypergeometric distribution is better modeled by a binomial. In other words, the sample size truly dominates what's going on rather than the proportion. Uh, so if you want to be consistent, it's better to have a consistent sample size even with varying lot sizes. So OC curve displays the discriminating power we saw OC curves in with control charts also, particularly Sheward charts where it's easy to do that. If we have a large N, we have, and P is our proportion defective, our probability of getting D defects follows a binomial distribution, which you might recognize here. And this is that combinations formula. Now, whether you want to remember that or use that for theoretical work, of course, you need the formula. In practice, you have a computer that'll do this calculation for you, and there are functions in Excel and R and Google Sheets that would allow you to do this calculation. So this is an expression there is the probability of acceptance for an NC control chart. So this is P sub A, or probability of acceptance, and this is what we plot on an OC curve as a function of P. What is the probability of acceptance? And so it can be done as a table. This is an 89 sample size, C is equal to 2, and this is our proportion defective, and we go from 0.05 down to 0.09, and that's our probability of acceptance. And then we could plot generally these on the x-axis and these on the y, and give us a fairly nice curve to interpret. And of course, at 0, this will be 1. So that's that curve. That's that table plotted as a curve. Lot fraction defective, probability of acceptance, and this is, of course, looks like an old style French curve kind of drawing rather than something done with a computer, but obviously that could be done. The effect of N and C on OC curves: probability of acceptance, lot fraction defective, an ideal OC curve. Now, ideally, we would say we accept a certain quality level, and ideally then the consumer knows that after the sampling plan is done, the parts come out, we will accept only a certain proportion defective, and we will reject after that, but not so. So this isn't ideal. This is in reality what we get. So you might find, now the problem is very often the probability of acceptance high probability acceptance is what is quoted as the index of the parts, and it's given the name acceptable quality level, or AQL, and that then people misinterpret that as the number that fits for this, and it isn't. So we could fiddle around with curves that have similar probabilities of acceptance at 0.01, and but have very different at, let's say, 0.04. If we have n is equal to 200, 100, or 50. We can play the game with, if we drop C, 0, except on 0, 1, or 2, we see we have radically different radically different curves. So bumping things upward on that or downward on that acceptance number changes our OC curve quite a bit. Now, the poorest quality level for a supplier's process that a consumer would be considered acceptable as a process average is called the acceptable quality level. So those that have high likelihood of passing are AQL. AQL is a property of the supplier's process, not a property of the sampling plan. Some of the older books put it as a property of the sampling plan. And the same with the lot tolerance percent effective. The protection obtained by of lots of poor quality established by the lot tolerance percent effective. So also called the rejection quality level or the limiting quality level, is a level specified by the consumer, not a characteristic of the sampling plan. However, given those, we can find places on the OC curve that we design an OC curve so that the LTPD is a certain high probability of acceptance, and the AQL, the LTPD is a low quality of acceptance, and the ALQL has a high probability of acceptance. So sampling plans can be designed to have specific performance at the ALQL and LTPD points. So that's what we do. We say this is the LTPD and this is the ALQL, and we say probability of acceptance at the ALQL is, and the probability of acceptance at the LTPD is. Type A and type B curves, we do the OC curves. Very often the ones we construct are assuming a binomial distribution. And those are moderately easy to calculate. The software is available. And they're actually not, at certain one point on an OC curve isn't even too terribly difficult for hand calculation with a modest level of C, for example. Now, the type B use a binomial distribution. The type A use a hypergeometric. And if I'm most of the engineering stats books will have hypergeometric distribution. However, some of the statistics books on a lower level won't have that involved, but the binomial distribution assumes we have an ongoing process and we can sample n of those. The hypergeometric distribution assumes we have a certain lot size with a large number n, and when we take away the and there is actually a finite number of defective parts in that large n. So the fact that there's a finite number of defective parts that's bounded differently than our sample size means that we have a different distribution than we would have in the binomial assumptions. So given the prerequisites for the class, this hypergeometric distribution might it's described in the textbook in the earlier chapters if you want to actually see what it looks like. Very commonly for this problem, in this setting, that when we get to cap n, the lot size equal to 2,000, it nearly overlays the system, and even it's the same as looks nearly the same as a binomial. I didn't go through the calculations, but the plots appear to overlay. Now, when we have as small as 500 parts, we see very little practical difference between the two curves in the range of the plotting space between them. Some other things. In the early 80s, there was and a bit earlier than that, there's a movement in quality called zero defects, and there were some folks that said if we have a zero defects plan, then we must have all of our inspection have a C of 0. Otherwise, we don't we're accepting uh, we're we're accepting defective parts, and we don't do that. Unfortunately, what some people had done is they use their current sampling ends and just set the C to 0 and was off with it. So they might be inspecting. Uh, so uh, they ended up getting some surprisingly sharp curves. Uh, I think we had, yeah. So if you had a C of 2 before and someone says, now we'll go to C equals 3 because we've got 0 defects plan, all of a sudden your curve looks way different and you'll start rejecting parts a whole lot more than you would otherwise. You can also tighten the inspection with a certain acceptance number by changing N. Um, someone might like the idea of 10% inspection, 0 defects, and that's how we're going to do things. What you want to do then is make your lots as small as possible. So I don't, uh, when you ship, because that idea of a n is equal to 10% and running the same sea level, you get radically different curves. That's um, so when you have as opposed to if you keep n fixed and c fixed and use that for a wide variety of cap ends, you don't get into much trouble, and we can see that there. Uh, for n equals 2000 or 500, the curves look almost identical, uh, independent of. We have another one. Yeah. No, I don't. So this idea of intuition, let's just take a 10% sample, and if we have a defect, we'll just reject the lot. Well, the lot size has to uh, having a large or small lot size can make a radical difference in the behavior of your accepted sampling plan. Uh, Now, 1 minus alpha level, we might want to set our beta as we did before. And then again, these are the probabilities of acceptance, and we can design our curves around those points, our N and C levels. Those you can pick N and then get a C to fit as closely as you want, and then adjust the N appropriately, and then or and then get some idea of what the beta looks like. And if that doesn't look quite right, so the probability of making a mistake, the probability of when you want the probability of acceptance high, probability um, when you want the probability of acceptance low, and here's where you want the probability of acceptance high, and can calculate those. Now, those calculations, sorting through those and trying to get some intuition on how you would do that. Yeah, if you had a spreadsheet, you could, generate lists kind of quickly on these um, uh, for N and C for these calculations. Now, with various levels P, um, but you'd like to develop some intuition on that. And however, there are nomograms, and what you can do is uh, you can you have a plot here where this is C and this is small n, and the lines run this way, and this nomogram allows you to design in this setting. We probability of C or fewer trials in N, probability occurrence in a single trial P. So this is our P term, and our small p proportion defective in our formula here. This is this P. And these are our probabilities, our cap P's. Do we have? Yeah. So this is our cap P probability of, well, our P sub A. These are our probabilities of acceptance. Our small p's are on the, these are what's on the right, and these are what's on the left. And what we then can do is when we, on this nomogram, and I don't really know the intuition of how this came about, but on this scale, we have our probability of acceptance, and we would maybe want a high value here when we have a low value there, and draw a line between the two. So we can design, let's say at 2% defective for the whole lot, and a probability of acceptance of 0.95. We could get a whole slew of sampling plans that would work for that. And how we can do that, we would use a straight line tool, and Annotate has a straight line tool. So how do we use this chart? Drag it out of the way and say at 2% defective, we would like 90% probability of passing. Right then and there. So we could lay our ruler off over this and see, do I? Yeah, it's probably better to use different colors here. So maybe have an eraser and I can erase this and go back to draw a line and I can have, so 95% chance that of being accepted with 2% defects. We can then get our 1 minus alpha 5%, and that at 2% we can design. And all of these plans cross. So anywhere that red line crosses, close to, we can pick an N and we can pick a C, and it all works. So our N's could be as small as 2 or so forth, and then our C that number of occurrences. Our C values can be as large as 20 or as small as 0 to achieve that on our 95%. So if we have, if we want to look at 1,000, we could have then 20 with a proportion defective of 2%. And when we want a probability of acceptance, if we had N is equal to 100, we would then set C is equal to 20. So we would sample 1,000 and take as large as, let's see, what am I? Can I go back to the mouse? Yeah, so this point, 2% effective, probability of acceptance, 95%. All of these plans where this lines cross could be done, and we can do it with as large, as small as acceptance level is 0, and as high as it looks like, I don't know, maybe 25 here, when N is equal to 1,000. Now you might want to, clean these up with some other calculations, but using this nomogram is pretty quick. The other thing is we might want to say, gee, at 10% defective, we really want a small probability. So at 10% defective, we want to make sure we only have like a 1% chance of accepting those parts, that lot of parts. Well, what does it tell us? It tells us there's only one answer that's going to work best for that, and that answer is going to be a little hard to read. It's there where they cross, and we can run our closest line up there, and that's between the 140 and the 200. Let's see, is that the uh, looks like have steps between 140, be 160, 180. So it looks like it'd be about 160, and then we run across the other way, uh, and it appears it's relatively small. So we trace that nearest line, which is this one, I believe, down and 4. So our plan would be uh, roughly N is 160 and C is equal to 4. This nomogram, yeah, makes it real quick to design things. Now, unfortunately, I only have the straight line tool. Okay, so let's see. Acceptance sampling plans require uh, corrective action when lots are rejected. So what do we do? Do we 100% inspect them? Do we send them back? When we have a rectifying inspection program, um, what happens if we do that? Entirely possible that if we reject a lot, we still want to keep production going. So we'll 100% inspect. Uh, we then would then realize that if we have this acceptance sampling plan, our rectified and acceptance lots will have a certain uh, a certain level of control based on what the actual percentages are. Uh, so the average outgoing stream is less than the proportion defective because every so often you're going to sort a lot. So it does clean up a bit. Uh, we can then look at this idea of rectifying acceptance and talk about an idea of average outgoing quality or AOQ. And uh, lots on the outgoing stage of inspection have probability of acceptance, P n minus, is the average fraction defective or average outgoing quantity. So we have some assumptions there. If we have lot sizes of n, we have so n is the sample that after inspection contains no defects. Um, because all discovered defects are replaced. N minus N, if the lot is rejected, contains no defects. N minus N, if the lot is accepted, contains P minus N defects. So our probability of acceptance times our proportion defective times N minus N gives us the average fraction defective, which is called the average outgoing quality, or AOQ. And looks like the formula in text. Yeah, so that's the expected number of parts. So we can express the average outgoing quality as that number, probability of acceptance times P times N. And we can have an AOQ function of P and N minus N, large and small n. So we can then calculate for each particular value of proportion defective small p, proportion non-conforming, the AOQ. It's tempting right now to say, gee, I know PA is a function that P sub A, probability of acceptance, is a function of small p. However, there's got to be some maximum level that we obtain at a certain p. So when n becomes large, cap n becomes large relative to small size n, we have a simpler formula for AOQ, very simple. And we get an we can have an AOQ curve here. So average fraction defective of outgoing lots, running that process long term, and having a rectifying inspection. There is a maximum point here, and it's, I don't know, 160% for 89C2, and we can have a maximum there, and it's called an AOQL. So that's what protection, our sampling plan, assuming we rectify inspections and send things through, send things out. And oddly enough, we get our worst outgoing quality at around 3% defective based on this. So what we then have to do to get this average total inspection, ATI, your average total inspection might be, labor dollars and equipment dollars. I remember, visiting a plant, was one of our suppliers when I worked for GE, and I think I saw 15 people just sitting, looking at parts and just sorting through them. It didn't look like quite the way to do things, but anyway. Just don't remember seeing that, uh, numbers of people having just a regular job, just sorting parts in a plant I worked in. Uh, as a regular job. So here's our average total inspection, and it's talked through. We'll have the small n for sure, and then probability of acceptance. 1 minus the probability of acceptance is this. So we'll have a average total inspection, and then obviously there's a max. Um, well, when the probability of acceptance goes to 0, everything goes to n. Average total inspection for various lot tolerances. It is possible to design rectifying inspection programs that have specific AOQLs. However, AOQL is not sufficient to determine the sampling plan. You can get the same AOQL that has different ATIs. Um, uh, Generally, it's unnecessary to go through the procedure because the tables of sampling plan that minimize A2I for a given AQL and specific processes P were developed by Dodge and Romek. And so AOQL doesn't specify things, and then you want to minimize A2I for a specific average P. Uh, uh, that kind of thing is in a set of standard tables that can be found. And it also can be set up for the lot tolerance percent effective. Those are the Dodge Romic tables. Never did that. So summary of 15.1, many characteristics of accepted sampling plans. Just a comment, control charts and design of experiments are now considered more important tools of quality than acceptance sampling plans. They were there. Our big tools are the OC curve, which gives us our probability of acceptance, our average outgoing quality, which is a function of the proportion defective and plotted that way for a specific sample size and acceptance level and NNC, and leads to an AOQL. And then we can also talk about the average total inspection as a function of our percent effective. So lets us know quite a bit. Double, multiple, and sequential. I've been rambling quite a bit. I gets me back to what I used to think about in the 70s when I was young and thin and poor. Well, I uh, I can't really say that. I lived in my parents' home, and we had working class lifestyle. Uh, which uh, so however, my own personal savings was not as high as it is currently. My own personal wealth but the lifestyle it supported was definitely not poverty. So double sampling plan, we have acceptance number for the sex and size and acceptance there on the second. And if we reject on the first, we go to the second. So that's the game for double sampling plans. Um, However, if on our first sample we have rejected enough total parts uh, to go beyond C2, we don't have to go take that second sample. We're already bad enough. So that's well, this is probably better than all that text. We have C1 and C2, and D is the number of defects observed. And if these are the specs here, except a lot if we get 1 or 2. Okay, so imagine we then take N N1 parts to an inspection station and observe D1 non-conforming parts. And if D1 is less than or equal C1, we go to accept. If D2 is less than or equal to C2, is greater than C2, we reject. If the third choice, and there should be a diamond here, right? This is not standard flowchart stuff. We should have a diamond with three points there. So if D1 is greater than 1 and less than or equal to 3. So if it's 2 or 3, then we inspect the second lot of 100 and we get D2, and then we make our decision to reject or not reject. If D1 plus D2 is if it's less than or equal to 3, we accept. If it's greater than 3, we reject. So that's how the double sampling plans commonly work. The most standard double sampling plans, you could have a few different rules, but that's the common one. Big idea is it might reduce total amount of inspection. This first sample in double sampling is smaller than for single sampling. If a lot is accepted or rejected on the first sample, the cost of inspection is lower. It's also possible to reject a lot without completing the inspection of the second sample. So double sampling, more administrative rules, less sample size. So probability of acceptance on the first sample. Now this is a chart I don't like because you have to read both the right scale and the left scale. So probability of rejection on the first sample has its own scale on it, and the probability of acceptance on the first scale and the probability of acceptance combined are on chart here. So this graph is sort of mistakenly overlaid here because it has a different scale. This is not probability of rejection. Okay. It, it isn't actually a different scale. Now that we look at this, the probability of rejection on the first sample is still probability of acceptance if you look on the left scale, because it's 1 minus probability of acceptance probability of not being rejected on the first sample is here. Probability of not being rejected on the first sample is here, and so forth. So we can see that when we have these higher defect rates, that it's very much likely that we're going to get things on the first sample rather than on the combined for rejection. Then we can calculate the average sample number in double sampling, and again, it's probability of making a lot deposition on the first sample. So probability of acceptance and probability of rejection. We then our new P1 has a very strange term, a definition, probability of it being accepted or rejected on the first sample is the term that we calculate. And of course, this average sample number will give us an average sample curve. I think that formula shows up a little curtailed. Now, curtailed is if we can achieve our acceptance or rejection numbers without actually completing our full sample inspection, then in the situation where most of the inspection is done in a sequential manner, this is important. One inspector taking apart and then measuring it in various places and moving it forward, doing sequentially, this makes sense. Sometimes the time equivalents of a test have to do more so with a full sample size. You might have to take all in parts and do something very time consuming with them before you can go on and do some things. So if we curtail the sampling rather than completed the inspection, we can really save our average sample number is much lower. So there's a comparison in double sampling if we go with a curtailed inspection. I might not finish this. Rectifying inspection. We have then rectifying rectifying inspections with double sampling. We can get an AOQ and an ATI just as we did before, and well, the more complicated functions, but they're still here, um, and we can trace those through. Now you can have multiple sampling plans that essentially work similar to um, an extension of the multiple sampling plans. Oh, somebody drop out? Six. No, check the participants. See if I can guess who. Ace, Kevin, Rosh. Oh, all right. Thanius isn't there. Somebody might have had a line drop or 8 o'clock ball. Okay. Sequential sampling plans. Yeah, we can just at every step we can go through um, our inspection, and we can go item by item or groups or so forth and have various rules. So sequential sampling, the systems do work for it, and usually these are shown with charts, H1 and H2, and we plot 2 lines, and essentially we have we count the number of defects and then the sample, and then as we go through, we plot things on our plots. So we inspected here till we got to 10, and we got our first defect. We inspected again till 12, got our second defect, and then inspected again up until 39 or so, and we decided to accept because it crossed our line. And this is a graphical performance of sequential sampling. And let's see if this book tells us. There are how to come up with, design these with alpha, beta, and K, and we KSP1 and P2. I suppose to illustrate, we have sequential probability P1 and P2 alphas. So we have our alpha and beta associated with our P1 and P2, and we just go through and work through the formulas here, and then we have S and H1 and H2 calculated from our tables, and then we can make our plots of our 2 lines that we draw, accept and reject lines. Instead of using the graph to determine, you can do a table too. Obviously, you from that graph you can generate a table. For sequential sampling, have some formulas there for um, average sample number functions and uh, so turns out we get a really kind of simple formula for our probability of acceptance. Uh, um, and then our rectifying, um, given the other characteristics of the curve, it simplifies quite easily. A rectifying inspection, we can have a formula for ATI and AOQ, approximate formulas. So the sequential sampling, although the theory seems like it'd be very intractable, when you work through it, the formulas are not all that difficult. Talking about this, Mill Standard 105E, and I guess there is something I could correct here. Uh, uh, kind of from an older edition of the textbook, and no longer ASQC. It's ASQ. They dropped the control in the acronym of the professional society. It used to be ASQC, now it's ASQ. American Society for Quality used to be American Society for Quality Control. And ANCI is American National Standards Institute, and they jointly have a version of Mill Standard 105D. And there is international version ISO standard for this too. We'll tell you a little bit about it and then show you what one page of the table looks like. It was sampling procedure for inspection by attributes developed during World War II and is the most widely accepted sampling, widely used and actually abused. And the collection of sampling schemes. Um, so it's actually a sampling system with multiple schemes in it, and it has 3 types of sampling: single, double, and multiple. The primary focus is on AQL. Um, different AQLs can be designated, and AQL then is the acceptable quality level. It's generally associated with a high level probability of acceptance, um, close to 95% in general in uh, in Mill Standard 105. Uh, we uh, different AOQLs may be designated for different types of defects for critical, major, and minor, generally specified in a contract or by authority responsible for sampling. The sample size is determined by the lot size and choice of inspection level. So those things are set up. We set up inspection level and sample size, and base things on what proportion defective we would generally accept. And before we actually look at what we do with Mill Standard 105E, why don't we just take a look at it? A new share, and we'll share the website and hide this. And I had this kind of a big thing. It's in Wikipedia. And notice that officially it isn't a Mills standard anymore. The And when I did this, you use the ANSI ASQ standard. So essentially, but this is the quick reference table, and this is nice of uh, what we have. We have make our decisions on what we're going to use. So general inspection levels 1, 2, or 3. And we then have a lot. Does that do anything? No, okay. That pointer. Let's say we have a lot of 1,000. And general inspection levels, are we in 1, 2, or 3? We're in inspection level then J, so then we go and find our H, J. Then our sample size we read is 80, and then we decide what our AOQL is, and our AOQL then, if we had an AOQL in percentages, AOQL of 1%, we then would have accept our C number would be 2 and our reject number will be 3. Now, we bounce around between these levels of tighten or loosen depending on history and some rules. So this is Mill Standard 105D. And when I worked for General Electric, these tables were just all over the place, and people used them. And they just said an AQL and had people use them. So uh, set an AQL, look up a lot size, say if you're what level you're at, and then if you're on tightened or uh, or loosened inspection, and go forward, pick your samples number, and you have no idea the underlying theory or anything, or scheme wise OC curves or anything like that. But just a master table for normal inspection. Um, and escape meaning 2 things for me, and new share back. And we have rules for the full implementation. For a specified inspection level, Millstep provides normal sampling plan to use as long as the supplier is at AOQL or better, switching between tightened or reduced inspection whenever the supplier's quality is changed. Then there are rules for when you go to tighten. So normal inspection is in fact, and tightened is when 2 of 5 consecutive lots has been rejected, on the original submission. So then we go to Titan. So we skip then to level 3. We can go and there's a rule of when we go back to normal, 5 straight good lots are accepted. And then we go from normal to reduced. Uh, and still, uh, and you have all these things are satisfied. You have to get an approval at the end. You don't have regular machine breakdowns. Um, the total defects from in the samples is enough, and then we run 10 lots and none rejected on the original. So a whole scheme of rules of going forward described. Um, and then we from reduced to normal, yeah, we follow 4 conditions, any of the 4 conditions, David's back. Discontinue inspections at a certain point. We're just go and say that we're going to stop inspection and whatever happens. So we have 5 rules of skipping between these, and there's a diagram of what to do between the different levels. Now, in practice, a lot of places use the mill standard tables and just say we'll run it normal and not use the full scheme. Is that wrong? Well, it's not a criminal act. You just have to state what you're doing carefully. We use them as reference tables and always stay on normal. Uh, so, uh, so step by step, start out with your AOQL. Helps to understand what an AOQL is, roughly. Choose your inspection level, determine your lot size, find the appropriate code letter from the table, and then the approved sampling plan. You either do single or double or multiple. That was a single page. Is there a double page too? Did they give us that? And escape, new share, and back there, share. Did we have? No. Sometimes they'll give you another page. Uh, uh, on the class I taught Monday night, they had multiple pages that you could go through. Here we had one, but the layout on the double sampling has a page that looks very similar to that. Uh, do I want to finish? Yeah, I hear my wife talking to my daughter on the phone. Yeah. Uh, Sample size codes, lot size, special inspection levels, general inspection levels, refer to tables in the textbook. Yeah. So more stuff of how to use a mill standard 105E in its full glory. Discussion, several points of mill standard 105E. Mill standard 105E is AOQ oriented, not all possible samples It's not all, it doesn't do all N. Okay, that's easy to see. It skips them out of convenience. Sample sizes are adjusted for lot sizes. Switching rules are subject to criticism, both of switching between plans and discontinuation, even though there is no actual quality deterioration. So there are the switching rules that get involved. And common and flagrant abuses of mill standard 105E is failure to use the switching rules at all. Uh, I we you can call it an abuse in flagrant, or you could just say we don't use mill standard 105B except for as a reference table. Not and if you're not actually dealing with a contractor that tells you you're going to use 105E in with all its rules, then you could be okay. That's it. Oh, Dodge and Romic. We roughly talked about, we talked about AOQL. So that limiting value, that maximum of average outgoing quality, and Harold Dodge and I don't remember Romic's first name, came up with these in the 30s, I believe, and they worked for AT&T, telephone company, and they had this problem. They had just warehouse full of parts, and they didn't like know how good they were, and they were just told to clean it up. So they just didn't want to inspect everything. So they came up with a procedure to do that, and this is where it comes out. And some relationship here between defective parts per million and AOQLs. So the AOQL systems are large compared to what people talk about now in parts per million defective. So not necessarily such a good idea. Oh, the tables. I guess the later work published in 1959, AOQ sampling plans for specified AOQ values, 6 classes of values for process average specified lot size, tables are available for single and double, designed that the average total inspection of a given AOQL and process is approximately minimum, and there's a table for an example. Now, we're somewhat telling you the following. Accepted sampling isn't so well regarded now as it was, early mid 80s, 70s. And I don't really know about earlier because I I just didn't ask. I guess any time after World War II, I assume. I, uh, and they're based on AOQL, which is a really, really intuitive, difficult calculation. But if we run it and rectify our inspection, this is how where we'll top out on defective rates. We've got a number, and it tells us this performance thing. And then LTPD, we're mostly a consumer, and we care about how bad the stuff can get in a in a how bad a defective level we're supposed to live with. So, and they run on those. Uh, now, LTPDs are at the right end of the OC curve, and uh, but the mill standard 105D. So these are more consumer and uh, more of a consumer's point of view of planning, whereas the AOQ are more producer controls. We want to make sure to hit the AOQL if we're in the mill standard 105D. So these are actually the consumer, and usually the person planning the inspection is the consumer. Uh, and so this is sort of what was done better and less popular, but there for academic concerns. A bunch of terms. Did we? I think we talked through most of those uh, terms roughly. And did we go through the learning objectives? Role of accepted sampling and quality, double, and uh, understand the structure. Um, I think we have some. I think I talked through most of those things. Thanks for listening. More news. Yeah, maybe a new link. There's a chance. Look for an email in the take-home exam. Did have I did agree to. I did agree to. I'll answer questions in the off week. Um, I'll answer questions next week. I'll answer questions next week during the early part of class time. Okay. Um, and formal statement and uh, look for take-home exam email. Okay. So much for that. So done for this week. Done for this week. All right. Thanks for hanging around. And boy, I thought I'd get done early, but I got it just at the bell. So escape. Uh, stop the goodbye to everybody. I'll stop the recording and